All right, so today we're going to be looking at significant digits to start our chapter 3. Whenever we take a measurement, most of the time we don't just stop with the measurement. We actually do a calculation. And this poses a very particular problem in science. And that is when we take a measurement, there is a limit to what we know. And this is different in math class because when I write the number 1.00 or 3.0, as you can see in this example, in math, numbers go to infinity. But in science, measurements have a stopping point because we are limited by the tools that we use. And so that kind of begs the question, when I take a measurement and do a calculation, if my measurement has a limit to it, then how in the world can I have an answer with an infinite number of decimal places? And the answer is, you can't. And so this is what significant digits helps us to explain. Is anything that we measure in the lab, these numbers, they have a physical meaning. And so the purpose of significant digits is to help us to know and to do our calculations so that we can pass along the uncertainty in the measurements that we take. And so before we can actually learn how do we do calculations with them, we have to first learn how do you look at a measurement and count the number of significant digits. And there's really just two rules. Number one, if there is no decimal point in the number or the measurement, you count from the first non-zero number to the last non-zero number. If there is a decimal point, again, you start at the first non-zero and you count to the end of the measurement. Let's look at some examples. So here, if there is no decimal point, then we go from the first non-zero to the last. So here we have 124. So I start at the 1 and I count to the 4, which gives me 3 significant digits. For the next number, I start at the 2 and I count to the 7 because I'm going from the first to last non-zero number. So that last 0 I am ignoring, which is how I get to 4. For 200, I'm only counting the 2. There's no decimal point, so the 2 is my first and last non-zero, so that's how I get to 1. And the last example, I start at the 1, go to the 5, and I get 2 significant digits. For rule number 2, if there is a decimal point, I start at the first non-zero and I go to the very end. So here in this first example, my first non-zero is the 2, and I'm counting all the way to the end. So I get 3 significant digits. So I now am counting that 0 at the very end. Here, for the second one, because there's a decimal point, it doesn't matter where the decimal point lies. You start at the 2, and you count to the very end, which is how I get 3. For my next example, start at the 3, count to the end, I get to 4. And for the last one, I start at the 2 and get to the end, and I get to 4. So zeros are typically a stumbling block when it comes to counting zeros, and you should be mindful that don't get caught up in the word significant. That doesn't mean it's not important. For example, 250 meters, which would only have 2 significant digits, right? No decimal point, just the 2 and the 5. That 0 is important because 250 is not the same as 25. That 0 is giving us our scale. But the issue here is you have to remember this isn't math necessarily. This is measurements. And when we take a measurement of 250 without a decimal point, there is some uncertainty there. Could be 240, it could be 260. But if that 0 were to be measured in the lab, well, we would put a decimal point there. This would be 3 significant figures, and this would communicate that the range is only plus or minus 1 as opposed to plus or minus 10 in the previous example. So those zeros are important, just sometimes they're significant, sometimes they're not. So go ahead and pause the video here and try to count the number of significant digits. Okay, let's look at the answers. And that's where you end up with. So again, we have rules. If there is or is not a decimal place, we have different rules of counting. Now, the reason this is important, again, is because it gets us to calculating. This is really the important part of why we have to do this, is because we usually calculate with our measurements. And our answers, our calculations, are only as good as our least precise measurement, right? You are only as strong as the weakest link. So depending upon what type of calculation we're doing, we have different rules. So when we do addition and subtraction, so let's look at an example here. So here we have 15.502 and 100 or 1.25 grams. To do this, we just add it together, which is 16.72 grams. Now, you have to remember that 1.25 is a measurement. So what's the number that comes after the 5? We have no idea, but it is a number. We're just not able to measure it. And so the answer is just assuming that the missing digit after the 5 is a 0. And this is the problem, and this is why we have to round. So when we do addition and subtraction, what we care about is the number of decimal places. So we have 3 decimal places versus 2 decimal places. So we pick the lowest, which is 2, and we round our answer to 2 decimal places. So 16.752. For 2 decimal places, it ends up as 16.75. If we're doing multiplication and division, we have a different set of rules. So here we have 10.25 divided by 2.7. When we divide, this is the answer we get, right? A whole ton of numbers. But the way that we round is we look at the different inputs. So this would have 4 significant digits. 2.7 would be 2 significant digits. And again, we are picking the lowest number of significant digits, which is 2. So we would be rounding our big long answer here to only 2 significant digits. So 3.796 blah 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 would round to 3.8. Let's walk through a couple of examples. So here I have 0.045 grams plus 1.2. I am doing addition. And so I care about the least number of decimal places. So my first input has 3, my second one only has 1 decimal place, and so I would be rounding my answer to only 1 decimal place. So 1.245 would be 1.2 grams. So let's look at a second example. So here I have 2.5 grams per milliliter times 23.5. This is what I get for an answer. I'm doing multiplication. And so what I care about is the number of significant digits, not decimal places. So my first input has 2, my second one has 3. I pick the lowest. So 58.75 rounded to 2 significant digits would be 59 grams. So here we have a third example. Go ahead and pause the video and see if you can get this one correct. All right, let's look at our answer. So here when we divide, this is what you will get on the calculator. And so I am dividing, so I care about the least number of significant digits. So this one has 4, this one has 3. So I should be rounding my answer to 3 significant digits. And rounded, that would be 0.427 grams per milliliter.